Can you map out all the islands in a complex network? Number of connected components in an undirected graph is a pattern mastery 100 essential. Frequently asked at Google, Facebook, and Amazon to test your ability to traverse graphs and count isolated clusters. Over 30% of candidates overlook singleton nodes or double count connections. Master this, and you'll be equipped for any graph or network connectivity problem. Let's solve number of connected components in an undirected graph using the basic method, so you never miss a node or count. Integer n, number of nodes, list of undirected edges. Integer, total number of connected components. Imagine mapping isolated local networks in a city, or identifying separate user groups in a social app. An interviewer might ask, how would you count all the isolated clusters in a computer network or database? What's tricky? Need to visit every node, even those with no connections, singleton components. Must avoid double counting, mark each node as visited as you explore. Both DFS and BFS work well here. Union-Find, DSU, is great for optimizing. Build an adjacency list from the edge list. Initialize a visited set or array. Loop through all nodes 0 to n1. If a node isn't visited, it's the start of a new component. Increment the count. Run DFS/BFS from that node, marking all reachable nodes as visited. Continue until all nodes are visited. Let's clarify. Single nodes with no edges count as their own components. Each DFS/BFS call finds exactly one component. Edge cases. Disconnected graph, multiple clusters. All nodes connected, one component. No edges, all singletons. Build an adjacency list from edges. Initialize a visited set or array. For every node from 0 to n1. If not visited, increment components count. Run DFS/BFS to mark all reachable nodes as visited. Return components count. Let's implement solution 1. Create a class solution to hold our method. This function counts connected components in a graph with n nodes and edges. Build an adjacency list. Each node maps to its neighbors. Loop through edges and add connections both ways since the graph is undirected. Set to track visited nodes. Counter for connected components. DFS helper to explore nodes in a component. Stack starts with the current node. While nodes remain to explore, pop a node and check its neighbors. Mark unvisited neighbors and add them to the stack. Go through each node. If unvisited, start DFS and count a new component. Increment components after exploring a full group. Return the total number of connected components. DFS explores each component fully, giving an accurate count efficiently. Efficient, simple, and elegant. Test input, 5 nodes, 0 to 4, with edges showing direct connections. What the input represents. 0, 1, and 1, 2, form one group. 0, 1, 2, 3, 4, forms a separate group. 3, 4. So, there are clearly two components. Why the solution works. DFS explores each node. Starts at 0, visits 1, 2, covering the first group. Moves to 3, visits 4, covering the second group. Each new DFS marks a new connected component. Program outputs 2, matching the expected result. DFS correctly counts connected components efficiently and accurately. Let's try solution 2. Union-Find, disjoint set. Define a solution class for the function. Returns the number of connected components in a graph with n nodes and edges. Each node starts as its own parent. Tracks tree height to keep unions efficient. Finds the root parent of x with path compression for efficiency. Merges sets containing x and y. Returns false if already connected, true if merged. Start with n separate components. Try to union each edge. If successful, decrement components. Return the remaining number of connected components. Time complexity. O(n plus e), initializing parent/rank is O(n), unions with path compression nearly O(1) per edge. Union-Find starts with each node as its own component, merges groups via edges, and efficiently counts remaining components. Simple, fast, and reliable. Test input, 5 nodes with edges, 0, 1, 1, 2, 2, 3, 3, 4. Each pair shows a connection between two nodes. All nodes are connected in a single chain, 0, 1, 2, 3, 4. There are no separate groups, so the graph forms one connected component. Why the solution works. Union-Find starts with 5 components, each node alone. Processing edges. 0, 1, merges 0 and 1 components. 4. 1, 2, merges 1 and 2 components. 3. 2, 3, merges 2 and 3 components. 2. 3, 4, merges 3 and 4 components. 1. No cycles detected, all unions succeed. Program outputs 1, matching the expected result. Union-Find correctly counts connected components, efficient, accurate, reliable. Let's have a quick recap. We're given n nodes and a list of undirected edges. A connected component is a maximal group where every node is reachable from any other. The goal: return how many such components exist, including single, isolated nodes. The challenges are thorough coverage and no double counting. We must visit every node, even those with no edges, and ensure once a node is explored, it isn't counted again. DFS or BFS handles traversal cleanly. Union-Find, DSU, is an efficient alternative for merging connections. Plan of attack: build an adjacency list from the edges. Keep a visited set/array. Scan nodes 0 to n1. When we find an unvisited node that starts a new component, increment the count and explore all reachable neighbors. Continue until all nodes are processed, then return the count. We followed that flow. Constructed the graph, ran DFS/BFS from each unvisited node, and marked nodes as visited to avoid repeats. The solution executed on LeetCode smoothly with no errors. We verified correctness by running through disconnected graphs, fully connected graphs, and cases with no edges. The logic behaved as expected and passed all LeetCode test cases. The core lesson: systematic traversal plus careful visited tracking turns complex networks into clear counts. Master this pattern, and you'll breeze through connectivity problems across graphs, maps, and real-world systems.